We are going to introduce now a very important definition, the definition of Cauchy sequence. So what does it mean? What is a Cauchy sequence? So first of all, of course, it's a sequence in a space X, in a metric space X. And we say that is a Cauchy sequence. Let me write down that this is a metric space. X metric space, comma, is a Cauchy sequence if for every epsilon there exists a number n, a natural number, such that for every n and m bigger or equal than capital N, one has that the distance between Pn and Pm is smaller than epsilon. Okay. So let's compare the definition of Cauchy sequence with the definition of convergence. They are very similar. Both of them have an epsilon there and they have a capital N. But if you notice, the definition of convergence involves a limit somewhere. Somewhere in the definition, there is a limit. In the Cauchy sequence, there is no limit. But instead, in the definition of Cauchy sequence, we have two indices. Here we have Pn and Pm. So what's going on here? This has a very easy interpretation. If we just look at the last condition here, that the distance between Pn and Pm is less than epsilon, because this is saying that for every epsilon, there exists some n such that the distance is less than epsilon. What we are actually saying is that the limit of the distance between Pn and Pm, as both n and m become large, this distance tends to 0. What we are saying is that a sequence is Cauchy if the terms in the sequence get closer and closer to each other as we progress in the sequence. Okay, that is the key point. The terms become closer to each other. In the definition of convergence, what we say is that the terms become closer to the limit. This definition of Cauchy is independent of the limit. And that is actually the power of this definition. Now, you may be wondering, so what is the relation between convergent sequences and Cauchy sequences? So we are going to see now a few results to get an overview, and then in the next video, we will show all the proofs. So the first theorem says that convergent sequences are Cauchy. Okay, well, Cauchy sequences, but sometimes you just say they are Cauchy. More formally, if we have a sequence Pn that converges in X, okay, then Pn is a Cauchy sequence. Okay, here again, I'm forgetting to say that this is a metric space, but this notion, because it involves a distance, will not make sense if we are not in a metric space. Okay, converges in X metric space, but it doesn't hurt to say, right? Again, because we are using the distance function, it has to be a metric space. So convergent sequences are Cauchy. And what about the opposite, the reverse? So are Cauchy sequences convergent? And the answer is, in general, no. Sometimes no. Okay. Let's say not always. For example, let's say I take x, that is the real numbers except for 0. Okay, and then I take the subsequence, sorry, the sequence, that is 1 over n. Actually, I can just write the 1 over n inside the brackets. This is my sequence Pn. Here, clearly, the sequence, this is not going to be a convergent sequence because the 1 over n is going to converge to 0 as n grows large, but 0 doesn't belong to x. And then we can always check that 1 over n minus 1 over m, okay, this is m minus n divided by nm. We can check that this becomes small, okay? This is as small as both n and m go to infinity. That's probably easier to see. It's probably easier to see that on the left-hand side, 1 over n minus 1 over m, if both n and m become small, that difference is also small because we are subtracting very small things. Actually, let's use the triangular inequality and then it's obvious, okay? This is as small as n m go to infinity, okay? So the answer is no in general, but that means that takes us to the next question, like, okay, if it's not always true, when is it true? Is it important? And it turns out this is a very important property and define what we call a complete space. A metric space is complete if every Cauchy sequence is convergent, careful here, in X. Okay, and I forgot to say that the metric space is called X. So a metric space X is complete if every Cauchy sequence is convergent in X. So in our previous example, it's clear why we call this complete, right? R, I took away 1 point, 0. Of course, it was not complete. Now, one example of a very good example is if we take X, that is the rational numbers, this is definitely not complete. You can design yourself a counterexample of some sequence of rational numbers that converges to, for example, square root of 2. So therefore, it will not converge within X, okay? But the sequence will be Cauchy, okay? All right. So give me examples of complete spaces. So these are the last two results that we're going to see. As I said, we'll prove this in the next video. The Euclidean spaces Rk. Well, Rk is complete. Okay, that's every Rk is going to be a complete space. That means that in Rk, every Cauchy sequence is convergent. Okay, but more in general, every compact metric space is complete.